A mass is suspended from a roof cable, X. It's then attached to a vertical wall by a second cable, Y. Obviously, this string is pulling to the right, too, because normally this mass would just be hanging straight down and it's being pulled to the right. So its weight is downwards, and there's a tension in this string holding it upwards. Those are all in equilibrium. If they are in equilibrium, they can form a closed triangle. In other words, everything is balanced. So I'm going to put colors onto those. Weight acts perpendicularly downwards. C and D are the only options with that as a truth. Force Y operates to the right. So we're down to pretty much to C, but let's double check ourselves. X operates towards top left. Yep, that's it. Oh no, yep, there we go. So C is the only one that complies with how we could draw for a diagram to represent those forces. A soccer ball is dropped from a height of h above the ground and it strikes the ground at a speed of v. Ignoring air friction, from what height must the ball be strike the ground in order to double that speed? If we use v squared equals u squared plus 2as, and it's dropped, so we can get rid of that altogether, and we can say that the acceleration doesn't change. So 2 and a are completely fixed in the story. So what are we going to need to do in order to double the speed? That's what we have to get. So we're going to 2 times v squared is equal to 2a and some or other unknown portion of s. So I'm going to go 4v squared is equal to 2a. I do not know how much higher I must go. And since I have put a 4 on that side, I must put a 4 on that side over there. On its own, a tow truck has a maximum acceleration of 3 meters per second squared. What would its maximum acceleration be while towing a vehicle of twice its own mass? So F is equal to ma, and that means that that acceleration, remember, is equal to force divided by mass. Acceleration is inversely proportional to mass, and therefore now if it's towing twice its own mass, it had a mass, plus it's now towing twice its own mass, so it's now 3 times the mass it used to be. If it's 3 times the 3 times the mass, you must have 1/3 of the original acceleration. 1/3 of 3 is 1 meter per second squared. The instant a steel ball is dropped from rest from a certain height, another steel ball N is projected vertically upwards from ground level. The maximum height that N reaches is the same height from which M is dropped. M does not bounce when it hits the ground. Okay, so we're coming down and we're going up. Consider the motion of N only for its rise upward. Which one of the following pairs of statements regarding the speed and acceleration of the balls is true when they are at the same height? Air resistance is negligible. For both of them, their acceleration is going to be downwards, and it's going to be exactly the same. So for both, the accelerations is downward. For both, downward, and therefore we down to deciding between the two. What happens now is when they are at the same height, so in other words, this one needs to have been gaining speed, this one needs to be losing speed, but they have been sent, another steel ball is projected from the ground level. The maximum height is exactly the same. So in other words, this is x, this is 0, sorry, this has been left off at 0 and is going to be x in the opposite direction. Because this distance is exactly the same and the acceleration is exactly the same through that journey, you're going to find that you've got exactly the same starting velocity, and this one would have the same ending velocity. And therefore, what happens is that they have an identical speed when they have the identical height, because that will be the point where they crisscross one another. A box is pulled across a horizontal floor by 60 newtons. There is a constant frictional force of 40 newtons. The box moves a distance of 6 meters. What is the work done against friction and the change in kinetic energy of the box? First, let us consider that work done is resultant force times distance. So the resultant force is 60 minus 40 because that's friction, so it's 20 times the distance of 6 meters. So that's equal to 120 joules. And that isn't even given to me as work done against friction, but it is given as a change in kinetic energy. Let's now think things through. Firstly, it's only the work done against friction. So I should only worry about the frictional force when I'm working out this work done. So work done is the force of friction multiplied by distance, which is 40 times 6. And that's going to be equal to 240. So that's right. Now, the net force is going to result in the change in kinetic energy, because kinetic energy is, change in kinetic energy is work done. Work done is energy transferred. So this net force over here is my change in kinetic energy. So A is the correct answer. We've got 2 kilogram masses traveling at 3 meters per second on a frictionless surface, and it collides head-on with a stationary 1 kilogram mass on impact. How much kinetic energy is lost in the impact? So the first thing that we need to do is we've got no kinetic energy at the beginning. We now know it is going to, and the masses stick together after the impact. So what we're going to need to do is we need to work out the whole change in momentum and everything first. So let's go. We're going to say 2 times 3 plus 1 times 0 is equal to, that's total momentum before, is equal to the new situation, and they are now going obviously at 2 meters per second in order for it to be equal. So after the collision, the velocity of the group is 2 meters per second of the two things together. Therefore, after the collision, the kinetic energy is equal to a half the mass of the system multiplied by 2 squared. So that is going to be equal to 6 joules. Before, we would have had a half mv squared, a half of 2 times 9, and we land up with 9 joules. So before we had 9, after we had 6, so what has been lost or transferred to something else is cars are designed so that sections of them collapse when there's a collision. These sections are called crumple zones. Watch statement helps to explain why crumple zones tend to reduce injuries. What they do is they still decelerate, the car still decelerates. However, it lengthens the time for that deceleration. And we know that change in momentum is equal to force times time. If I make the change in momentum doesn't change, but if I make the time bigger, the force of impact would have to get smaller. So that is what's taken. So the deceleration of the car's, the time taken for the car to come to rest is not reduced, it is lengthened, okay? The rate of change of momentum, so that means that I need to divide by time, and that is force. Rate of change of momentum is force, so the force is reduced, and the loss in kinetic energy of the car is reduced. I don't think this links to kinetic energy in any way whatsoever. So they're going to ask you what is going to be true. The car's deceleration, rate of change of slowing down is actually, if you think about it, the deceleration is going to be, it's going to be over a longer period of time. So that deceleration is reduced somewhat, okay? So therefore, B is my correct answer, 1 and 3. The identical conducting spheres are carrying charges of 3,2 and 3,2 times 10 to the negative 19 and negative 6,7. The spheres are allowed to touch. During the touching, X gains how many electrons? So we're going to say plus 3,2 minus 6,4 means that it becomes minus 3,2. I have to divide that in half, and I get minus 1 comma 6. In other words, sphere X has gone from plus 3 comma 2 to minus 1 comma 6. Times, all this is times 10 to the negative 19, obviously. And that means that the change is 4 comma 8 times 10 to the negative 19. And if I divide that by the charge on one electron, which is 1 comma 6 times 10 to the negative 19, it would have been 3 electrons that have been transferred. Fabio conducts an experiment to investigate the effect of a magnet on a solenoid. As shown in the diagram, he pushes the magnet towards the solenoid, and the meter connected shows a deflection to the left. What is the deflection when the magnet is pulled away at the same speed? It's going to be exactly opposite, so it will be to the right. And it's the same speed, so it will be exactly the same deflection. In the diagram below, a conductor is placed between two magnets carrying a coil. What direction is their force? So now we need to take your left hand. You stick your first finger from north to south. Put your second finger out of the page. That is a dot, so it's an out of the page. So put your second finger out of the page, and you will notice that your thumb points towards the 1 over here.